Hi guys, this is Counting Methods Lesson 5. It's combinations. So I've been warning you in the last couple lessons that you need to understand that in permutations, order matters. When we get to combinations here, we will see that order no longer matters. So a combination is a selection where order is not important. Sorry, I kind of crossed out stuff there. So this is how it's different from permutations. So in permutations, order matters. So this is lining up for things or arranging things. The one thing that is really confusing is if you have a locker at school and you have a lock on it, whether or not you use your lock, we call that lock a combination lock, but it is not actually a combination lock. It is actually a permutation lock. Because if your password for your locker is 52711, you cannot put in 11275 because that's not the right order. So those locks on your locker should actually be called permutation locks because the order actually matters. So that's kind of a confusing thing, and hopefully I didn't confuse you more by telling you that, but it is not a combo lock. It is a permutation lock because order matters. So a combination is something like me going to Jugo Juice and getting a Jugo Juice slushy thing. Milkshake? Not really. Slushy. So it does not matter if I get banana, strawberry, pomegranate, or if I get pomegranate, strawberry, banana. It's the same thing. They're putting them all in. The order that they go in that thing doesn't matter because it gets all whipped up and it doesn't matter. Or if I'm choosing a group of people to do something, so I'm choosing 3 people out of 10 to be on a committee or something like that, the order does not matter. They're all in that next group, so it doesn't matter. So that's the big thing with this. So it says, for example, the 2 objects A and B have one combination because AB is the same as BA. Their order is not important. So I don't know what this in the brackets. I don't know what that actually looks like here. So order does not matter. I don't remember what in the last lesson actually had that. So it says if n objects are taken r at a time, then the number of combinations can be calculated at. So this is NCR. So with permutations, we saw NPR, and this is n objects arranged, or this number of them arranged of the total number, something like that. This is saying if n objects take an r at a time. So again, the calculation that your calculator does for this is n factorial, so that's your total number factorial, divided by n minus r factorial and r factorial. So this is what your calculator does. You can do this step every time if you want. I'll probably do it for like one question, but do the calculator steps instead. So again, in the TI calculators, so sorry, Jax, hopefully you've figured out how to do it in the Casios. I know if I had one, it's actually pretty easy to find, but I don't remember exactly where it is. So it's in the same place as permutations. Oops, so same place as permutations. So you put in whatever your n value is, and then you press math, and then you scroll over, I think it's 2 scrolls, to PRB, which is probability, and then it's number 3, and then you put in whatever your R value is. So that could be like 15C. That's what this gets you, saying find the combination of 3 objects out of 15 possible objects. So using your calculator for something like that, just to practice. Let's say, yeah, let's give a weird smoothie example. We went to Jugo Juice. There are 18 possible flavors, or 18 possible like flavors of fruit. And I want to make myself a smoothie that has 4 of them. So how many different smoothies can I make? So I can make strawberry, banana, kiwi, peach, which is the same as peach, banana, strawberry, kiwi. Again, the order doesn't matter that they go in. Or I could make pomegranate, apple, carrot, banana, or something like that. So there's lots of different combinations. So again, just double checking that you know how to do it in your calculator. So there are 18 possible options. I'm trying to choose 4 of the possible options. So you put in 18 and then you press math. You scroll over 1, 2, 3 times, I guess it is. Press number 3. So on the TIs, it should say 18 NCR, and then you press 4, and then you press enter. So that gets us 3,060 different smoothies that I could choose from if you could just choose whatever. But we know at Jugo Juice or any of those smoothie places, they have set menu ones, so it's less than that. They don't have 3,000 things on their menu. So sometimes you'll see this, just if it ever pops up. If you ever see, I'm trying to think of, maybe it comes up on one of the worksheets. Sometimes you'll see it written as just in like regular brackets, whatever your n is over whatever your r is. But you don't write it as a fraction, so you don't draw that line in between. So in the case that we had there, it will just say 18. And when it's in this, we know that we're talking about a combination, not a permutation. It's just a weird notation that sometimes can pop up. So the first one, it says, consider the number of possible lottery tickets that can be created from playing Lotto 649. So what Lotto 649 is, for those of you that are not yet 18 and haven't bought a lotto ticket, or those of you that realize that playing a lottery is a little bit of a waste of money potentially. Lotto 649, there are in total 49 numbers. So you can choose the numbers 1 through 49, and you get to choose 6 of them. So some people choose all of their family's birth dates or their lucky numbers or something like that. So me, let's think what I would choose. I would choose 11, 12, 22, 6, 7, and 8. So that's in all of those, it encompasses me and my family's birthdays. So those are the 6 numbers I would choose. It doesn't matter what order I choose them in. So I could choose 8, 11, 6, 12, 22, and 7. It doesn't matter what order they actually come in this case. So the first question says, why is this situation a combination rather than a permutation? Oh, I just explained that. So the order of the numbers is not important. So again, those lotto tickets are the same. So if I did that the way I had here, it doesn't matter. They're the same thing. So determine the number of possible tickets. So how many possible tickets could we make if we wanted to scam the system and buy every possible ticket? Say the jackpot got up to, I don't know, $2 million, and I was like, you know what? I want to win that $2 million. How many different lotto tickets would I need to actually be creating? So the number of possible tickets. So we know there are 49 numbers, and we need to be choosing 6 of them. Again, the order doesn't matter, so we're not doing a permutation, we're doing a combination. Just in terms of that formula that we wrote in the box up above, remember that that represents 49 factorial over 49 minus 6 factorial times 6 factorial again. Sorry, my family's being very noisy right now. That's a pain in the butt to put in my calculator. I could do it, but I'm going to do just that 49. Press the math button. Then scroll over 3 times. Probability and then number 3. And then put in 6. I'm going to actually do this. 49 math. Scroll over. 49 NCR6 gets me a total of so I would just need to buy just under 14 million tickets to maybe win $2 million. And I think tickets, I don't know how much a Lotto 649 ticket is. Is it $5? So 14 million tickets, $5. You're looking at a heck of a lot of money. So it costs you about $70 million to buy all the tickets. Plus it would take forever, right, for them to print all those tickets off. So, and the other thing with lottery, sorry, I'm going to just kind of scroll down, that again, it's all based on probability. So the winning ticket of 1, 2, 3, 4, 5, 6 is as probable as 12, 9, 18, 22, 43, and 37. These both have the same probability of winning. Nobody ever picks this one, like chooses it. It can get picked out of the drawing. So remember, the drawing is a random drawing. I think they do it with balls. So there's 49 balls in a drum, and they stir it up and eventually pick the numbers out. So nobody ever chooses this. I say nobody, maybe people do, but this is it would be as probable to win as a random assortment like this. But again, nobody ever chooses that one, but it could easily win. So the lottery's a hoax. Well, it's not a hoax, it's real, but it's a little bit difficult to win. So it's saying, in how many ways can 17 songs be chosen from a possible 38 songs? So this one is a little bit hard to think about. So it's saying, how many ways can 17 songs be chosen from a possible 38 songs? So this question is not asking us for a playlist, because in a playlist, order would matter. It's just saying, let's choose in total 17 songs out of the possible 38 songs. And again, it's not giving us an order. These questions are a little tricky. I don't like songs questions because sometimes you can kind of justify that it might be a permutation over a combination. But since it's just saying chosen and not arranged or a playlist or something where order would actually matter, we know we're going to be doing a combination here. So 38, C17. Again, what that represents is 38 factorial divided by 38 minus 17 factorial times 17 factorial gets us so there are, you know, just a couple trillion, I would think. That number is trillion. A couple trillion different ways that 17 songs can be chosen from a possible 38 songs. So 38, I just want to double check. Oops. Yeah, so 2.878, so on, times 10 to the power of 10 ways that we can choose 17 songs out of a possible 38. And again, the order doesn't matter. So question 2b here is kind of giving us the differentiation of how many, or how is this different from the number of 17 song playlists that can be formed from 38 songs. So when we're talking about a playlist, now order matters.
right? You want, if you're trying to get people out on the dance floor at a wedding, you need some pump up songs at the beginning and then maybe some slow dance songs and then some more pump up songs. But in order will eventually matter for a playlist. Or when I'm going for a run, I need my most inspirational song when I'm dying after 1 kilometer because I'm very out of shape. So an order matters for a playlist. So for 17 song playlists, now we're going to do a permutation of this. So 38p17. So you're going to put that in your calculator, and instead of pressing number 3, you're going to press number 2 for permutations on the TI. So we get 1.02 times 10 to the power of 25. And that's the number of options for playlists. So hopefully you understand why a permutation and a combination are different. You need to ask yourself, does order matter? Does it make a difference? So question 3 here. It says, if a committee of 7 people will be formed from a pool of 12 people. So if you watch The Office, maybe it's the party planning committee or something. It doesn't matter in this case. When we're talking about like committee questions, the order doesn't matter. You have 12 people and you want to get just 7 of them. So it doesn't matter who was picked first or last or anything like that. You just end up with a smaller grouping of them in the end. The order doesn't matter. So in how many ways can this be done? So we have 12 and we want to choose just 7 of them. So there's 792 ways for this to be done. So it says if Steve and Nick must be on the committee. So Steve and Nick need to be on our party planning committee. So Steve and Nick are already chosen. So now we need 5 more people from the remaining 10. So there were 12 people, but we know that Steve and Nick need to be on it because they're the best party people. So we need to pick 5 other people from the remaining 10. So that will be 10C5, 252. So there's 252 ways to have committees of 5 people out of the remaining 10 if Steve and Nick need to be there. So the next one says if Steve and Nick must not be on the committee. So Steve and Nick are not good at being on committees. They're a hot mess. But so ignore what we've said for the first 2, but now we need Steve and Nick not on the committee. So now we have 10 people to choose from because Steve and Nick are no-goes. So that's 12 minus Steve and Nick, which is 2. So 10C7 because we still need 7 people on our committee. So there's 120 ways to create those committees. Yeah, so that's what combination questions can look like. So next one. So in a group of 11 employees, there are 4 men and 7 women. So in an office or in a job somewhere, there are 4 men and 7 women. It's pretty close to kind of our teaching staff. I think there's about 15 people at our school, 15 staff, and we got 4 guys and the rest are women. But unrelated, it says determine the possible number of 5 people committees. So it doesn't say anything about gender. It's just saying we want to pick 5 people out of these 11 people. So that would be 11C5. So there's 462 possible combinations of 5 people committees out of these 11 employees. It says question 2 says determine the number of possible 5 people committees that consist of 2 men and 3 women. So this and means we need to multiply. I can't remember if that's come up yet, but I think it has. When we see and in these types of questions, we're going to multiply. When we see or in the next question, we're going to add. And we'll see that more with the or question. I'll explain it out a little bit more. So 5 people committees that consist of 2 men and 3 women. So 2 men, 3 women. So that adds up to 5. So the way that we can get 2 men, so we know we are 4 men and we want to choose 2 of them. So 4C2 multiplied by 3 women. So there are 7 possible women, we want to choose 3 of them. So 4C2 multiplied by 7C3. So 4C2 is actually equal to 6. 7C3 is actually equal to 35. So 6 times 35 is 210. So there's 210 ways to have 5 people committees that consist of 2 men and 3 women. So the next question, says determine the number of possible 5 people or 4 people committees. So when we have an or question, it's saying how many ways could we make committees with 5 people, or how many ways can we make committees with 4 people. So we know our 11C5, we already figured that out up above, that's 462. So if we didn't know if we wanted to have a 5-person committee or maybe a 4-person committee is better, what we can do is we can figure out how many different options are there where we could have one or the other. So 11C4, I think is, what did I write down, 330? And so that gets us 792. So again, if we're talking about an or question, we're going to add. If we're talking about an and question, we are going to multiply. I think your next one, it should say the labeling principle. We're going to skip over that. You can peek through it and see if you can figure out what it is, but we're not going to talk about labeling ones. Labeling's bad, right? So we'll go on to question 5 there. So it says a student council of 5 is formed from a selection pool of 8 boys and 9 girls. So student council makes some decisions. There are 17 people that want to be on it. That comes from this. So 17 people. And it seems like it's just a random drawing of who gets to be on it. So 17 people want to be on the student council. It can only have 5 people, so there's a random drawing. It's not based on who's the best at anything. So how many committees will have all girls? So all girls, so in total we have 9 girls. So we want to know 9C5, because there are 9 girls. We want to have the whole student council be girls. So there are 126 ways, or 126 committees that can be formed using all girls. 4 girls and 1 boy. So again, 4 girls and, so we know when we have an and, we're going to multiply 1 boy. So 4 girls is 9C4, because we want to choose 4 girls out of the possible 9. And then we want to, there were 8 boys, and then we want to choose just 1 of them. So 9C4 multiplied by 8C1 is 1008. So there's 1008 committees that would have 4 girls and 1 boy. Oops. I thought there was one more question for that one. Question 6. How many games are necessary in a tournament of 30 teams where each team must play each other once? It's worded a little bit funny, but this is saying, I don't know, it's a ping pong tournament and there are 30 teams and everybody needs to play every other team. So I, as team number 30, need to play 29 other teams. And then whoever's number 29 needs to play everybody else, but we've already played against me, so we kind of are taking that out. So This one's a little bit hard. I can understand that this is confusing from the start. So 30, we know there are 30 teams. In one game, there needs to be 2 teams. And again, team 30 playing team 1 is the same as team 1 playing team 30. So we would go 30C2. So there would need to be 435 games going on. That's insane. So that's why in big tournaments, they'll usually have like a round robin where there'll be group A and there's 5 people in it and they all play each other, and then group B has 5 teams and they all play each other, and then the best of those come out and play each other in the end. So because trying to organize 435 games to find a champion would be a little bit insane. So onto standard deck of cards questions. So a standard deck of cards. Again, you should know kind of oh, sorry. I thought I missed a question. I'm losing it. Standard deck of cards, so 52 cards, 4 suits of 13 cards. There are 26 black cards and 26 red cards. So you should know all of these details. You should know your black cards are spades and clubs. Red cards are hearts and diamonds. So it says, how many 5-card poker hands are possible? So if we're playing poker, because we decided that the lottery was not enough gambling for us and we wanted to play poker now, it's saying if you have a standard deck of cards and they were shuffled up all nicely, how many different, if you were dealt 5 cards, how many different combinations of cards would there be? Again, order doesn't matter. So when you play poker, they deal them out to everybody. The 5 cards you get, though, the order doesn't matter which card you received first and which card you received second. You get it and you reorganize it anyway. So order doesn't matter with card stuff in this case. So in total, again, a standard deck of cards, there are 52 cards. And we are looking for a 5-card poker hand. So there's just a mere 2.5 million 5-card poker hands that are possible. That's not very many. So that's saying if you dealt poker hands, it would take you 2.5 million, almost 2.6 million to deal the same hand again, potentially, probability-wise. It could happen one after the other just based on random probability, but there are in total 2,598,960 possible hands that you could be dealt. In how many of these hands would you be dealt all diamonds? So you get dealt them. How many ways are there that all your cards could be diamonds? So this is called a flush. It would be a flush in diamonds in that case. And that's a pretty good poker hand. You can make money off your friends by getting that. So all diamonds. So again, we know there are 13 diamonds in a deck. So 13, C5. So in that 2.5 million, 1,287 of them are dealt as all diamonds. Because again, we're choosing a 5-card hand out of the 13 possible diamonds. So the next one, it says, in how many of these hands will there be 4 black cards and 1 red card? So black cards and red card. So 4 black cards, again, we know there are 26 black cards in a deck. So we want to be choosing 4 of the black cards. Since it's an and, we know we're going to be multiplying 1 red card. So again, there are 26 red cards. We want to just be picking one of them. of those 2.598 million possible poker hands, 388,700 will have 4 black cards and 1 red card. So again, just double checking that you're putting these in your calculator right. So 26C4 will be 14,950 multiplied by 26C1 will be 26. I can't remember if your notes have this. Sorry, I'm just going to check if your notes are the same as mine because I know I've modified this. Counting methods booklet. My computer's being crazy these days. Did I add in? Okay, I'm going to go on. Actually, do I want to do? We would have seen this. I guess I didn't really define it. Sorry, I'm just looking at my notes. Okay, let's go to question 8. That's fine. So at a Justin Bieber addiction meeting, so those people that are super hooked on the Biebs, there are 300 handshakes. So everybody, it says how many people are at the meeting if every person shakes every other person's hand once. So before they start the meeting, they say you need to shake everybody's hand. So how many people are at the meeting if every person shakes every other person's hand once? This is a complex situation. Like this is a little bit hard to recognize from the start. So what we need to think about is we have NCR, so the number of people at the meeting, and we're going to have a handshake. So a handshake involves 2 people, so it's going to be NC2, and in total there are going to be 300 handshakes. So you could, if you came up to one of these, you could plug in chunks. So you could put in 200 C2 and see what you get your answer. You could put in, you could be like, oh, that's way too much. You could put in 50 C2, see what you get for your answer. But I'm going to show you the algebraic way to actually solve this, or what this actually represents. So again, NC2 equals 300. So again, we're choosing 2 people for a handshake. It doesn't matter if I shake your hand or you shake my hand, as long as we're both participating in that handshake, the order doesn't matter. So what I want to represent that as, I want to use that formula that we had back on the other page in the box. So that was n factorial divided by n minus r. So n minus r, n minus 2 factorial times 2 factorial. And that's equal to 300. So now some of that factorial notation back in, I think it was lesson 2, what n factorial represents is n times n minus 1 times 1 less than that, which is n minus 2 times n minus 3, dot, 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 and so on. On the bottom, we have n factorial, or sorry, n minus 2 factorial. Oh, I don't want to actually write that factorial part. So n minus 2 factorial represents n minus 2 times n minus 3, and so on and so on and so on. And 2 factorial represents 2 times 1. So what I see, I'm going to change my color here just so that it becomes slightly more clear, is we have n minus 2 times n minus 3 times so on, times so on, times so on. So what I'm actually going to do, I didn't realize I could do this. I feel like I just changed my life by just writing in here. We can cancel this out since this is a factor in both my numerator and denominator. So now what I have, oh my god, look at this life, guys. N times n minus 1 over 2 times 1, which is 2, equals 300. I'm just going to make this crazy. We're going to have so much fun. So now what we can do is we're going to solve this like a quadratic eventually. So I'm trying to get n by itself. I'm not going to be able to because it's n times n, so we're going to get an n squared. So what we want to be doing is collecting all of our terms on one side to solve as a quadratic. So I'm going to multiply both sides by 2. So now I have n times n minus 1 equals 600. I'm going to, what does this do? Distributive property. Whoa. Oh, it gives me weird dotted lines. Okay, we're not going to do that again. That's weird. So distributive property, so n times n is n squared. N times minus 1 is minus n. And I'm going to subtract 600 from both sides. So n squared minus n minus 600 equals 0. So now I could either do this graphically or factoring or quadratic formula if you wanted to. So by factoring, you can practice this, two numbers that multiply to negative 600 and add to negative 1. So that's going to be n minus 25 and plus 24. You could do your box method, whatever you want to do there. But these two numbers multiply to negative 600 and they add to negative 1. So now analyzing which of those make it true. So our answers for n are positive 25 or negative 24. We can't have negative people. That's weird because you totally can have people that are negative, but in this case it's asking us counting wise how many people are there. So there are 25 people at JBeeb's support meeting. I suppose this is supposed to be like an I here. So there are 25 people and they all need to shake each other's hand. So you need to be shaking the hand of 24 other people if you're attending that meeting. The last one, I think it has it on your sheet. I don't have a slide for it though. So if it doesn't, you might just want to listen. So it says prove or verify that nck equals n times c n minus k. So what that's saying, I'm going to just use a random example. So 5, oh no, let's do a bigger number than that. 7c3. So in this case, I've called n equals 7, k equals 3. So 7c3 is equal to, so 7c, so n minus k, so 7 minus 3 is 4. So it's 7c3, and we're saying it's equal to 7c4. So try putting those in your calculator quick. So 7c3. So that's equal to 35. I don't know, I'm punching this in my calculator. I know that it actually works. So why are those the same things? So thinking about what that actually represents, so say we have 7 people and we want to choose a committee of 3 people. So there's 35 ways to choose a committee of 3 people. If we had those same 7 people and we wanted to choose a committee of 4 people, there's 35 ways to choose the committee of 4 people. So what that actually represents, and this is a little bit of a hard concept to wrap your head around, is it represents, so if you think in this one, if we're choosing 3 people, a committee of 3 people, what we're actually kind of doing is choosing 4 people to not be on the committee. And that's what this kind of represents, right? 7C4, what we're actually doing in this case is choosing 3 people to not be on the committee. So when order doesn't matter, you choosing a number out of a whole number, so choosing your particular number out of your total, is equal to not choosing that same number out of the total. So what that actually represents, oh, sorry, give me a sec. Sorry, trying to do stuff with children around is quite the issue. I had to pause it there for a second. So I don't even know what I was saying right now, but choosing 4 people to not be on the committee is the same as choosing 3 of the people to be on the committee. So algebraically, just to kind of explain that out, this is like a super complex thing to understand, but thinking about our formula that we had before. So again, it was on the last page. I think I used the letters N and R, so NCR is equal to n factorial divided by n minus r factorial times r factorial. So let's look at those 2 situations. Actually, I'm not even going to use the numbers. I'm going to just use the letters that we had there. So we have NCK and NC n minus k. So in terms of this equation, so what that represents, so my k is the same as my r, so n factorial over n minus r factorial times r factorial. Oh, sorry, I should be using k's here. Whereas this one is n factorial times, sorry, divided by n minus, so in this case, my r is n minus k. And my r here is n minus k again. So looks like a hot mess. Haven't really proved anything, but let's just think about, again, we're not using numbers in this case. I just wanted to show you with the numbers here that it would actually work out, but this is actually proving it algebraically. So, oops. I'm going to actually just leave this as is, but I want to do some simplification here. So n factorial on the top. So n subtract n minus k. So thinking about this, so this negative is going to be distributed throughout it. So now on the bottom, what I would have is n subtract n plus k factorial times n minus k factorial. So I can do a little bit of a further simplification there. I should be using all my fancy colors. Let's do that quick. So distributive property here. Again, the important things here were my r value was equal to n minus k. I'm really backtracking now that I'm using my colorful pens. So n subtract n is 0. So now what I have, n factorial, so n subtract n is 0, so we just have k factorial. So n factorial divided by k factorial times n minus k factorial. So what you'll see now these are the same. N factorial on top, K factorial on the bottom, N minus K factorial on the bottom as well. So this we proved algebraically. Why this is actually true. We kind of verified it with this, or we saw an example. We could do a whole bunch, right? We could do 11C6, and we would find out that it's the same as 11C5 because of this whole algebraic process to solve it. So again, choosing one number. So choosing 6 people to be on a committee is the same as not choosing the other 5. So that last one probably has blown your mind a little bit, but you guys are smarty pantses, so you got this. So your practice questions are on the next 2 pages. I think there's an answer actually on the very back page, but I might have updated some of the questions. So I would check my key that's posted on D2L. You'll have a permutations and combinations assignment next week. So, oops, I'm just going to scroll down. So when you hit those ones, again, ask yourself every time, does order matter? So these are organizing, like organizing things in an order. So arranging, lineup questions, whereas combinations, whoa, this is a long lesson, holy smokes. Combinations, order does not matter. So committees, like drawing random numbers or something like that. Lots of card questions like poker hands and stuff like that, but you need to ask yourself at the beginning, does order matter in this case? So I know that was a long lesson. Maybe take a break and then do the combination questions tomorrow. I think I left 2 days for you guys to be doing combination questions. Yep, again, next week you'll be getting the assignment and you'll have a quiz on it. So good luck. You know how to reach me if you need help.